Before I kind of start, let me just give you a brief introduction about our speaker, and then I would formally hand this over the session to him. So, for the man who doesn't need any introduction, who is also a part of corporate team, is our presenter. Is none other than Mr. Ranjit C, who is also heading the structures teams in our corporate office. Okay, so he would be the speaker for today. Okay, and also, just to give a brief intro about him, Mr. Ranjit he has completed masters in structural from the College of Engineering Trivandrum, Kerala. He carries total 23 years of experience in the field of structural analysis and design. The major projects he has handled review and approval of major and important railway bridges of DFCC project. Today he is here with us to present about analysis and design of abutment of a railway bridge. So I'm sure you all are excited equally for this session with our very own speaker, for our in-house speaker. Okay, so with all that, I would formally welcome Mr. Ranjit sir to take this session forward. Sir, over to you. Thank you, Mr. Mahendra.
Good afternoon, everyone. My topic for the presentation is analysis and design of an abutment for a railway bridge. So to start with, let us see what is a bridge. A bridge is a structure which carries a road, pathway, railway, etc. across a river, road or other obstacles. Bridge is constructed to cross an obstacle that everyone knows. So when it is crossing a road, it is called a road bridge. When people are crossing over the road, it is called a foot over bridge. And when a railway is passing over the bridge, it is called railway bridge. That is about a bridge, which is crossing an obstacle. And there are different types of bridges based on bridges can be classified into different types based on the material, based on alignment as per location, for the purpose, type of superstructure, according to span and navigation purpose, loading, life of structure. So like that, bridges can be classified into different types. Coming to the first one, material. Everyone knows the type of material used for the construction of the bridge. If it is RCC, then it is an RCC bridge. If it is masonry, that is stone masonry or brick masonry, it is a masonry bridge. Or if it is made of steel, then it is called a steel bridge. And if it is made of timber, it is called a timber bridge. Or if it is made of composite sections, it is called a composite bridge. So bridges can be classified based on its materials. So then type it can be classified based on the alignment. Suppose if it is the bridge which is in a straight alignment, it is called a straight bridge. And if it is in a skew alignment, it is called a skew bridge. And as per the location of the deck, so deck is where the traffic moves. So if it is the deck is at the superstructure at the top, then it's a deck bridge. And if it is at the bottom of the superstructure, then it is a through bridge. Otherwise, if it is between the bottom and top, the placement of the deck, then it is called a semi-through bridge. So you all know the steel railway bridges. It is through bridge. The deck is coming at the bottom. And the road bridges, that is deck bridges. And semi-through bridges are also there. These are based on the placement of the deck. And type of span. It can be a continuous bridge. It can be a integral bridge or simply supported bridge. So that is depending on the type of support condition which is provided. Most bridges are simply supported bridges. It is easy to analyze and easy to construct. That is the reason the most of the bridges are simply supported bridges. Simply supported bridges, the major issue is the expansion gap. So that easiness of movement. So you might have noticed while you are crossing a road bridge. So unevenness is there. So in order to avoid that, we can have continuous bridges so that expansion gaps will not be there. So, but that need to be designed for the uh, additional forces due to temperature and all. So that is called integral bridges. And other type of this cantilever bridges or these are the depending on the type of support. It is called cantilever bridge or type of support condition. And then based on the purpose, it can be aqueduct, viaduct, grade separators, highway bridges or railway bridges or footbridges. And according to HFL also it can be classified. It can be a submersible bridge or non-submersible bridge. And according to lifespan, it can be a temporary bridge or a permanent bridge. And according to the load classification, for example, for bridges, road bridges, it can be class A bridge, and all. It is based on how much load it can take. And for railway bridges, basically it is 32.5 ton or 25 ton loading. Normal our railway traffic is for 25 ton loading. And for DFCC, for the goods carriage, the minimum standard is 32.5 tons. Like that, and lift bridges also is there. For example, our Pamban bridge, where there is a lift span is there. When a ship comes, it can be raised and ship can move. After that, the railway or the road traffic can use the bridge. That is called lift bridges. So these are the different types of bridges which can the type of bridges which can be classified into different categories. So our topic is railway bridge. In railway bridge also, because we are basically dealing with only railways. So our topic, what I selected is a railway bridge, and for railway bridge also I am limited to my topic into a abutment. Abutment is a structure at the end of the bridge. So you might have seen different type of bridges. So at the two ends, the structure which is supporting the span and the embankment, that is called the abutment. What are all coming in between? If there are n number of spans, that is called piers. So in bridges, one is at the end, supports are with abutments, and at the middle, all those are piers. So now I think this is clear. So now coming to the specifications. Standard specifications, because there should be some we cannot design a bridge as per our interest and as per our uh, requirement. It should be based on some standard specifications. In India, this highways and railways are owned by and controlled by the government of India. So accordingly, IRC and IRC specifications are relevant to road and railway bridges. So bridges need to be, bridge design need to follow these specifications laid down by IRC or IRS. IRC is the specifications for road bridges, Indian Road Congress, that is IRC, which is to be followed for the road bridges, and IRS, Indian Railway Standards, is the specifications which we have to follow for the design of railway bridges. So that is about the specification. Okay, each country has its own specifications. Okay. And now coming to the main parts of bridge. Bridge having different parts are there, but the main parts of a bridge are foundation, substructure, and superstructure. basically the foundation which transfers the load of the superstructure and substructure to the ground. That is called foundation. So we decide the foundation based on the geotechnical investigation. So geotechnical investigation is taking a borehole and understanding the nature of the soil below the ground. So based on that an analysis of the geotechnical report, we understand that what type of foundation can be provided. And depending on the load, if it is for a small bridge, and then we can go for open foundations. If it is a long span bridge, definitely there may not be sufficient bearing capacity to go for a open foundation. Then we have to go for pile foundations, or in like river Ganga, we may have to go for, we cannot do this piling, we have to go for well foundation. That are the basically the foundations. Major foundation types are open foundations, pile foundations, and well foundations. So that depends how we are deciding the foundation for a bridge is depending on the geotechnical recommendations and based on our load requirement. So from that we are deciding the type of foundation. Next, coming to the substructure. Substructure is above ground level and below the superstructure. That is called a substructure. So, means it is a pile and pile cap. It can be below ground. So that can be the foundation, and above the pile cap, whatever structure is coming below or up to the pedestal level is called a substructure. So the function of the substructure is to transfer the load of the superstructure to the foundation. It is actually acting as a medium between the superstructure and foundation. It is transferring the load from the superstructure to the foundation. So that is the function of substructure. And next is above the substructure. So means above the pedestal in pier cap and abutment, you might have noticed the pedestal. So above the pedestal, bearings will be there, and on top of the bearings, the superstructure will be placed. So function of the superstructure is to take the load of the vehicle passing on top of it and to take its own weight. That is called the self weight of the structure. So that is the function of a superstructure. So foundation anchors the bridge to the ground. The substructure supports the superstructure, and the superstructure is the part of the bridge that carries the load of the truck. And this is the figure showing this, whatever I told. Foundation is the structure below the ground, and the substructure is between this, whatever coming between this pedestal and the structure above ground level is called substructure, and the structure above the pedestal is called the superstructure. These are the main parts of the a bridge structure. There are so many other parts like wing walls, bearings are there, railings, parapet, all those crash barriers. Those are all my parts are there, but these are the major three parts of a bridge structure. Now, foundation I already explained. This is foundation and how this is transferring the load. And what is substructure? Its purpose is to support the superstructure and distribute the load to the foundation. Key elements are piers and abutments. Piers are generally vertical, generally, not always, that supports the deck and transfer the load to the foundation, and abutment structures at the end of the bridge that support the deck and transfer the load to the foundation. That is at the end. Basically, abutment is if it is a multi-span bridge. If there are n number of spans, the abutments are at the two ends. Those two structures are called abutments. And the other in-between structures which is supporting the superstructure are called piers. Our topic is on abutments. So we should know what is abutment. Abutment is at the two ends of the bridge and which is supporting the superstructure deck and transfer the load to the foundation. In addition to that, actually it is supporting the earth behind the structure. And superstructure, the main purpose of superstructure is to carry the traffic load and to provide a road pathway or railway. Key components: deck, girders or beams. And deck is structure where vehicles travel, often made of concrete or steel. Girder or beams are horizontal structural members that support the deck. This is called superstructure. So everyone is seeing the superstructure basically when we are traveling over a bridge. So this is our topic, abutments. So this two circles which are highlighted, these are the two structures called, it is a single span bridge. In single span bridge, there is only abutment. If there is multiple spans, then there will be abutments and piers. So these are the two end supports. These two end supports are called abutment. So abutment is the structure at the end of the bridge span supporting the superstructure. Single span bridge have abutments at each end that provide a vertical and lateral support for the span, as well as acting as a retaining wall to resist the lateral movement of the earthfill of the bridge approach. This is about the abutment. If it's a single span bridge, then there will be only two abutments. There will not be any pier. And it provides the vertical and lateral support for the span. Vertical means the weight of the superstructure that is acting vertically downwards. That is called the vertical load. And lateral load is due to seismic forces, due to wind forces. That are the lateral forces also need to be need to be need to be resisted by the structure. So that is lateral force. And in addition to that, the one more purpose, basic purpose is it has to retain the earth behind the structure. That is the earth pressure it has to retain. Pier, the difference between pier and abutment basically is it is not, abutment is retaining the earth fill behind the abutment. Pier is not retaining, basically not retaining this type of earth fill. It is only to support the superstructure, dead weight and lateral forces. That is the difference of abutment and pier. Okay. Now, I think it is clear. So for abutment, basically abutment, for the analysis and design, abutment following are the basic loads to be considered. First is dead load and SIDL. Second is live load. Third is dynamic augment, longitudinal forces, frictional resistance, earth pressure due to surcharge, buoyancy effect, wind pressure effect, seismic forces, forces due to curvature or eccentricity of track. These are the major forces which need to be considered for the design of an abutment. So dead load and SIDL. So dead load is the self weight of the structure and the self weight of the superstructure. That is actually the self dead load of the dead load to be considered for the design of an abutment structure. SIDL is the superimposed dead load. So, for example, for in railways, railway bridge design, SIDL is the load due to track, sleepers, rails, ballast. These are the components which is contributing to SIDL. So that SIDL load also will be transferred to the abutment. So one is dead load and the other is SIDL. For the design of abutment, this dead load of the superstructure and SIDL are readily available in the RDSO drawings. So we can directly take the dead load and SIDL from, for different spans, for different RDSO drawings are there. We can readily take it from the RDSO drawings. If it is not a standard span, then definitely there will be a superstructure analysis. So for the superstructure analysis, we will get the support reactions. So that for the support reaction for the dead load and support reaction for the SIDL. That reactions we have to apply to the abutment structure for the analysis. So this is the first load, that is dead load and SIDL, which is taken for the analysis of a abutment structure. And for road bridges, similarly, the dead load of the abutment and the load of the superstructure of the road bridge. MOST standard drawings are there. Otherwise, superstructure analysis results will be used for calculating the dead weight of the superstructure and SIDL of the superstructure. And live load. Live load is the load of the traffic or for the road traffic, or for railways, it is the load of the live trains passing through the which is utilizing the bridge. For example, for DFCC, the loading will be 32.5 ton axle loads, and for the normal railway traffic passenger trains, it is 25 ton loading. So that is the load. So, and for road bridges, the loadings are as per IRC 6. It is clear what are the loads to be taken. For example, class A load, special vehicle loads, class 70R loads. For these are all specifications. So the axle loads are clearly mentioned in that one, and the axle spacing also is there. So based on that, we have to find out how much is the reaction coming on this abutment. So that is about road. And for railway, live loads are directly available in the IRC bridge rules. That the table is clearly depending on how much span live load EUDL is clearly. So it is easy comparing with the road bridges. It is readily available in a table format. Suppose if our span is 12.2 meter span, so then we can read the table, how much is the reaction at the total equivalent uniformly distributed load is available. So the reaction we can taken means the total load divided by 2. If it is a single span bridge, that will be the live load reaction, which is to be taken for the analysis of an abutment. Now, dynamic effect for road and railway, these both are actually the moving loads are passing over the bridge. So when it is moving on the bridge, it is having a dynamic effect. So to simplify that, both the railways and roads have given how much live load we have to increase. Suppose if it is 100 tons, we have to increase the live load by a percentage. So that is called a dynamic effect. Dynamic effect is called coefficient of dynamic effect is readily available. Equations are readily available in the IRS bridge rules. So we can follow that, and the live load need to be increased for the dynamic effect. So that also need to be added to the whatever load which previously we are taken live load. That live load need to be multiplied with a factor called dynamic effect. So that is called dynamic effect, and the coefficient how to find out is 0.15 plus 8 by 6 plus L. L is the span of the structure, and it can be subject for a maximum of 1. It will be less than 1 only, but it should be subject to a maximum of 1. So that is called a dynamic effect. Now, longitudinal forces. Longitudinal forces both in road and railway, there is tractive and braking forces are there. So we have to take it into consideration. So that tractive effort is there when train is on the bridge and it is at rest condition and it starts from there. There is a tractive force, and when it is moving and it is stopping at there is a braking effect is there. So these are also how much is the load to be considered for the tractive force and for the braking force, depending on the span of the structure which we are dealing for the analysis. It is clearly available in the bridge rules. So depending on span, we can take the longitudinal force for tractive force and for braking forces. So from that, we will get the longitudinal force due to tractive and braking force. And another longitudinal force is resistance to the movement of bearings due to change of temperature. So it is not 100% flexible. There is a resistance for the bearings, which also will produce a force on the structure. That also we have to take it separately. And forces due to continuation of LWR or CWR forces, long welded. So long welded forces means if it is simply supported, it can, if it is, the rails are not joined together, so it is free to expand over the bridge. If it is not, if it is welded, if it is not, if it is connected over the bridge, means it is not free to expand over the bridge. So it will in, exert a force on the structure. That is called long LWR forces. So that is called, that will make a horizontal force which we have to take into consideration for the analysis of the abutment structure. Now, frictional resistance of expansion bearings. So these expansion bearings, so what is the purpose of bearing? Actually, we have to transfer the load from the superstructure to the substructure. There is a mechanism. So that is called, actually the transfer is through bearings. There are different types of bearings. Usually elastomeric type bearings are there. Then metallic bearing, port PFE, port PTFE type bearings. So different types of bearings are there. Depending on the loading and the load to be resisted, the type of bearings we have to decide. And that bearing is not fully free to expand. So the fully free to move. So there is a friction. So due to that friction, there will be a resistive force. That force also act as a horizontal force on top of the abutment. That is called frictional resistance of expansion bearings. So how to calculate all those things are clearly given in IRS bridge rules. So for different types of, for roller bearings, how much the coefficient is 0.03. For sliding bearing on steel, on cast iron or steel bearings, 0.25. Like that, we have to find out the coefficient and we have to find the force to be taken for the frictional resistance. That also will act as a horizontal force. Next, major force. These are all, whatever I explained, are from the superstructure and the self height of the structure. The other additional major force which is acting on an abutment is the earth pressure. You all might have seen that abutments are retaining the earth fill behind it. So earth always exerts a pressure on the abutment, and how much it will be exerted, that will also act as a lateral force on the stem of the abutment. It's like a stem on the cantilever retaining wall. Now it acts as a when this is considered, it is like a cantilever. It acts as a stem. The abutment wall will act as a cantilever retaining wall stem. The action will be like that only. Earth pressure will be exerting, the abutment wall will be bending towards the traffic direction. So how much is the force? that is W and H is the pressure, half into that one will be the total force, and K we have to multiply with the K, coefficient of active earth pressure. So earth pressure diagram, how it is exerting is clearly given in IRS bridge rules and in substructure code. So, and the factor K is equals to cos squared phi minus alpha by cos squared alpha into cos alpha plus delta into 1 plus root sine phi sine phi plus delta into sine phi minus. So that is the equation. So we have to, reading that figure, we have to find out what is phi, what is alpha and all. We have to give the inputs and we will get, usually it is 1 by 3 K. To be precise, we have to, for a bridge design, we have to exactly calculate how much is K. So that is the active earth pressure. If you get the active earth pressure, we know how much is the weight of soil. It is usually 19 ton, 1.9 ton per meter cube or 19 kilonewton per meter cube. And H is the height of the earth fill, which is supported by the abutment. So it is easy to calculate the earth pressure exerted on the abutment stem. That is regarding active earth pressure. So active means then in the same equation K will be active earth pressure, and passive means for the same equation you have passive pressure is half into W into H square into Kp. The Kp is the passive pressure coefficient. The difference is K is replaced by Kp here. Okay, usual cases we are taking the active pressure only. Railway is not allowing to utilize the, actually it is a relieving effect, passive pressure, but railway is not always allow us to take the advantage of passive pressure. So it will resist the active action. So in some cases we will utilize this passive pressure also to make it the calculations correct. So that is passive pressure. Now earth pressure due to surcharge on abutments. That is also a major load on the abutment. Surcharge is actually the on the abutment structure, this dead load of the rail, sleeper, ballast, everything is on the backside of abutment. That is called a dead load surcharge. It is above the acting above the abutment. That is dead load surcharge, and when train is passing on top of the structure or top of the abutment, what happens? It will also exert a additional load in addition to the earth pressure. That is called actually surcharge. Additional to the earth pressure, an additional load is coming on top of the structure. This is called surcharge. The surcharge is two types, due to the dead load surcharge, and the other is live load surcharge. So live load surcharge we cannot directly calculate. So railway has given how much we need to account in the analysis. For DFC loading, it is 16.3 ton per meter cube, and for 25 ton, it is 13.7 ton per meter, and the width it is acting is 3 meters. So this is directly from the IRS substructure code. It is clearly mentioned in the code how much you have to add in addition to the earth pressure what we are calculated. So earth pressure on top of that surcharge is coming. Surcharge is, there are two types. One is dead load due to the ballast and sleeper and all. It is permanently acting on top of the fill of the abutment, that is dead load surcharge. And when train is passing, there is a live load. In addition to the earth pressure, there is a live load surcharge is acting on top of the structure. That is called the live load surcharge. Dead load surcharge and a live load surcharge we have to add it. Additionally, we have to apply on the model or take into consideration for the analysis. That is surcharge. Now buoyancy effect. So when there is major bridges, and major bridge means which is crossing a stream. So that is called major bridge, and whose span is more than 12.2 meters. That is major bridge. It is crossing a river or nalla. So in that case, water can come near to the abutment, and based on the HFL, high flood level, this some part of the structure can go below the water level. So then whatever we are calculated earlier, that dead weight, when it is water level is coming there, then its weight will get reduced. That is called buoyancy. So why buoyancy is required to calculate? Because we have to check the abutment for overturning, sliding and all. In that case, we are taking full weight of the structure, full weight of the dead load of the superstructure and all. Then this buoyancy may reduce the actual weight. So may not satisfy the our stability criteria. So what railway specifies that you have to take the buoyancy effect also into consideration. How much part of the structure is going below HFL, and that part it is to be considered for buoyancy effect. Buoyancy, when something is inside the water, its weight will be less than the actual weight. So that how much is the difference, that only you have to take into consideration for the analysis. That is called buoyancy effect. And wind load. Wind load is the actually the lateral force which is coming and acting on the superstructure and on the live load. So that will be acting in the transverse direction. So that load is a lateral force on the abutment structure. So how it can be calculated? It is clearly, the steps are clearly mentioned in IS 875 part 3. The how much at each location, how much is the wind pressure, and based on the wind pressure, how much intensity of force will exert on the live load or will exert on the superstructure part and on the substructure part. So that force we have to take into consideration for the analysis of the uh, abutment structure. That is a lateral load which need to be taken into consideration for the analysis of abutment structure. Now, for another lateral force is the seismic force, which is also a lateral force, and longitudinally also it will act. So that is due to earthquake. That load also need to taken into consideration. But there are some exemptions. Slab bridges, box and pipe culverts need not be designed for seismic forces. For design of substructure of bridges in different zones, seismic forces may be considered as given below. Zone 1 and 3 seismic force shall be considered only in case of bridges of overall length more than 60 meters. So in seismic zone, the India is classified into zone 2, zone 3, zone 4 and zone 5. All India is, entire India is in different zones. So the intensity will be maximum at zone 5, seismic intensity will be maximum at zone 5 and lesser will be at zone 4 and still lesser at zone 3 and least at zone 2. In latest codes, zone 1 and 2 are merged. So zone 2 will have the least seismic intensity. Depending on that one, zone factor we will get. So we can calculate how much is the seismic force which is exerting on the abutment structure. So if it is less than 15 meters, it need not be taken into consideration. So that is about seismic force, which is also a major force for the analysis of the abutment structure. So, and the other force, which is due to curvature and eccentricity of track. In railway code, it is very clear, even for ballasted bridges, even on a straight track also, we have to take a minimum eccentricity of 100 mm, and we should consider that also. If even though this bridge is on a straight track, so we need to take 100 mm eccentricity for the load, and that need to be applied on the model which is going to analyze. And due to curvature, if the alignment is not in a straight path, there is a curvature. Depending on the curvature, there will be a lateral force. So mv square by 127 r is the equation to calculate that lateral force due to curvature. And where the lateral force is acting, that is clearly mentioned in code, the horizontal load due to centrifugal force, which may be assumed to act at a height of 1.83 meters for 25-ton loading, and for DFC loading, it is 3 meters. This is about the load due to curvature of the track. So this curvature produces a centrifugal force on the moving vehicle. So that load will be transferred to the substructure through the bearings. So that also need to be considered for the analysis of this abutment structure. Next is force due. And now these are the major forces which broadly I explained. These are the major forces which are to be considered for the analysis of a abutment structure. So, and now loads are taken: dead load, SIDL, curvature load, buoyancy effect, wind load, friction forces. All these loads are listed, calculated, and applied in the model. And after that, what we have to do is load need to be combined. So combination is based on the combination rule. See, it is clear that for an abutment, definitely the earth pressure is acting always. And when there is no live load, the load means when there is no train is passing on the structure, on the superstructure, the load which is acting is earth pressure and the self-weight of the structure and the self-weight of the superstructure. When train is running, that time all these additional loads, the live load will come, the lateral load due to wind will come, so other loads also will come. So how this need to be combined? So there is a combination, there is combination rules are there, and it is clearly indicated in the substructure code. There are different combination 1, 2, 3, 4, and 5. In this different combination, the different loads will be combined, and its worst effect or its effect will be accordingly calculated, and the structure will be designed for the worst effect. So which load combination need to be considered for the design is that also is given guidelines are there. Based on that only we are designing the structure. So that is about the load combination. Now analysis of the structure. So these loads, basically we may make a Midas model or a stat model, or sometimes Excel sheets are used. These loads are applied on the structure, and that will be analyzed to find out how much is the internal forces, how much maximum is coming, internal forces are coming, and for that internal forces we have to provide the required material. Material means if tension is coming, concrete is not able to take more tension, concrete is very weak in tension, that part will be reinforced with the steel reinforcement for RCC structures. So they are the part of steel reinforcement. Where the tension is coming, that part will be provided with steel reinforcement. These abutments are basically a cantilever. It is like the action is similar to a cantilever retaining wall. If you know the design of a cantilever retaining wall, the abutment design is very simple. Cantilever retaining wall, what happens is earth is supported by the stem, and the stem is bending towards the other direction. So tension is at the earth face, and the major tension reinforcement is coming at the earth face, and minor or the temperature reinforcement or the minimum reinforcement will be provided on the other face, and the distribution reinforcement. The bottom slab is a two components, toe side and heel side. Earth side, the bottom raft. Earth side is called heel side and the other side is called toe side. Maximum pressure, base pressure will be coming at the toe, at the bottom. So tension reinforcement, it will bend up, and hence the reinforcement at bottom on the tension side of the toe slab. And for heel slab, it will be usually at the top of the rough slab or the base slab, and the detailing will be done accordingly, and minimum reinforcement also will be there. So in usual case, this will be a pile cap will be provided for the abutment structure, and below that piles will be there. So that is about the analysis and then the design of the structure. So simply it is a cantilever retaining wall. So this is the simplest way what I am explaining this abutment analysis and its design. So let me share the screen to show you the drawings of an abutment. This is done by BARSYL and approved by NIT, Andhra. So this is what I explained. So this is the part of abutment, which is called abutment wall. And below that, if it is a pile foundation, it will be a pile cap. And below the pile cap, piles will be there. These are the major part of the abutment, and this is the superstructure. And V-poles in abutments, why V-poles are to release the water pressure behind the earth retaining side. Earth may have water may happen, water level may increase, and water may exert pressure on the wall. In order to avoid it from our calculation, V-poles will be provided so that water pressure will be released from the abutment wall. So this is called V-poles, and this is the abutment wall. This is the pedestal which is supporting the bearings, and on top of bearings, superstructure will be resting. And this is inspection slab, and this is pile cap, and this is pile. And this is the layout of the piles. Abutment cap, bearing pedestal, and bearing, how it is supported. And this is the sectional view where it is showing the superstructure is supported on top of the abutment wall. So this is the, and behind that wall, there will be return walls will be there. So the section of this return wall is this one. So the detailing of the reinforcements is like this. This is for the pile that everyone knows, and this is actually what I explained for the abutment. So it is like a cantilever structure. So if it is a cantilever abutment wall, so major reinforcement will be the vertical reinforcement, and this is the distribution reinforcement, and this is the pile and its pile reinforcement. This is actually the detailing. So and how it is presented. So bar number 1, 2, like that, the reinforcement will be presented. This is also abutment 1 and the other side abutment 2. This is the sketch of an abutment. So this is a design report. In design report, this is the sketch is for this is showing the piers. So this is the design analysis and design of the abutment wall design report. This is the sketch what I was explaining. Pile, on top of that pile cap, then abutment wall, which will be on top of that abutment cap will be there to transfer the load, then pedestal and bearings, then return walls. So this is actually an Excel calculation of the analysis. So whatever this is that surcharge calculation, what I was explained, surcharge calculation, then surcharge pressure on pile cap. So like that, we can make the analysis in the Excel. And then it's design. This is the report of this is the complete report, around 49 pages. The report is there to explain the details of calculation of the foundation analysis and design. And now we have software is also there. Whatever I explain, we can do it directly from the software. So here the complete structure can be modeled in Midas. So this is pile, then pile cap, then this is pier and pier cap. So everything can be modeled. This is actually not abutment, this is pier. This is also a substructure, but this is pier. So everything can be modeled, and the loads, we can directly give the loads here. Static load, self weight is, so self weight we can give, then nodal loads. Display. So these are the different loads. So that we can directly give through the software. So it can directly analyze all the loads we can give, and load combinations also we can directly apply, and it can analyze the structure, and it can directly design also. Design, and we can get the reinforcement. So that can be utilized for making the drawings. So all loads, this is actually the dead load, static load, and then display different loads and different cases it is applied, and it can be analyzed. So that is the software application of the substructure analysis and design. So hope my explanation somewhat clear to you for the abutment analysis. So any questions are there, you can ask to me or you can mail to me. I will try to explain you. And thank you everyone for attending my presentation.
So there is one question posted by Anand sir on
Yes, sir.
the chat.
Yes, sir. How do we consider
Do we consider catenary effect on the bridge?
That is actually, it is, the question is regarding the superstructure. We were explaining the design of a substructure only. So this superstructure part is different, and we are talking about the substructure. Substructure is the part of the bridge which is supporting the superstructure. This will be taken care in the analysis of the superstructure.
Okay.
Yes,
Okay. All right. Team, any other questions? Anybody has
Ranjit
any
ji,
question?
yes, sir.
this is I want to ask one question regarding RDSO standard bridges
Yes, sir.
design.
Yes, sir.
So, when client says that the the design is standard RDSO design, it has to be copied and replicated across. So, does that mean that design is available, uh, and you don't need to design anything?
If it is a standard span, for example,
Ah,
12.2, 45.5, the standard spans are available.
okay,
That drawings are available, then we need not to do the superstructure design. We have to
okay,
take the dead load and SID. It is clearly mentioned in the drawing how much is the dead load, SIDL loads are from the superstructure. That we have to take directly from the drawing, and we have to apply it in our substructure model. So
okay.
superstructure is standard, then railway is mostly following standard spans. They are not allowing you to have a um, um, different span. Mostly we have to follow the standard spans. Otherwise, we have to do the analysis of the superstructure, and from the superstructure, we have to take the loads for the analysis of the substructure. If it is a standard span, no need to do the superstructure design. Only substructure we have to design.
Only substructure. And what
Only
about the
substructure.
live load? What about the live load configuration?
Yeah.
Mm.
Live load actually, if suppose if we are referring the RDSO drawing of 12.2 meter or whatever standard span, live load also it is clearly written in the drawing itself. In addition to that, we can verify it in the IRS bridge rule. In IRS bridge rule,
Mm.
uh, depending on the span, shear span, how much is the total uniformly distributed load coming on the span that is there. Suppose if it is 12 meter, if it is 100 ton, then on the abutment it will be 100 by 2. That is 50 ton will be acting on the abutment. There are two options. Either you take it from the RDSO drawing, or you can cross verify it uh, with the IRS bridge rules.
No designing modification or no STAD modeling needs to be done for that.
No,
STAD or
no,
no
no,
be done.
no, no,
Okay.
no, no. Nothing is required if it is a standard span. We have to do only the substructure design and analysis, substructure analysis and design.
Okay, fine.
Okay, sir.
Looks like there are no more further questions, Ranjit sir. I
Thank you.
think we can close it here. But
Mm.
thank you so much from the entire BARSYL attendees who have attended this session. So thank you so much for delivering this session, and we look forward for for sessions from you on other structural topics as well in coming days. So
Thank
thank you
you.
so
Mhm.
much.
Thank you. And any questions, you can send a mail to me. If I'm not knowing, I will take help from others or from our team also is there. We'll answer. We'll try to answer you. Anything is there, it will be benefit for us also. So you can send any questions to us through mail. Okay, anytime. Okay. And thank you for attending my presentation. Thank you.
All right. Thank you,
Thank you.
everyone. Thank you so
Thank you.
much.
Thank you.
Have a great day. Bye bye.
Thank you.
Thank you.